To kind of close things out today, let's talk about geometry and what linear functions look like, or how we can think of them geometrically, or how we can read off geometric information. So if we've got a linear function, it's a certain special type of function. It takes in m input variables, m real numbers, and produces n output variables. And we've already seen a couple of these when we were looking at previous lectures. One of those is parametrized lines. If we have a point and a direction vector, we can construct a function that takes in one input and produces, three outputs. That parameterizes the movement of an object along a line inside space. Or if we had a point and two direction vectors that were parallel to a plane, we constructed a parametrized plane instead that spanned out, took in two inputs and produced three outputs, and told us all the points that were on that particular plane. Now, we have more interpretations than that, but these are two that have shown up for us already. And we'd like to understand a little bit about some of the general features of linear functions like this. So there are two main parts. There's a vector b and a matrix A in a linear function. The vector b is a translation vector. It tells us where we start. It's a start point that says, when I feed in 0 as my input, where do I end up? And if we move the vector b around, if we change it, that is the effect of changing kind of the whole effect of the function by translating it. It just shifts it over to one side or another. Correspondingly, the matrix A is kind of a direction. When we saw parameterized lines, we had a direction vector. And when we had parameterized planes, we had two direction vectors that told us the two kind of independent directions that we could move on the plane. More generally, the matrix A, the column vectors of this matrix A in a linear function are direction vectors. They tell us what direction we move if we change different input variables. If we change the first input, we change in the direction of the first column vector. If we change the second input, we change in the second direction of the second column vector. So let's be a little bit more picturesque about this. So here on the top we've got a parameterized line. We have the origin and we have the point 1 here. When we look at this output, the parameterized line B has the start point, and the direction vector V is pointing in the direction of this line. Whereas at the bottom, for a parameterized plane, the origin 0, 0 is mapped to the vector B. If we change the first input, the x variable, we move in the direction of the x arrow. And if we have a change in the second input variable, y, we change in the corresponding direction that goes with the second column of the linear matrix. So that's the things we've seen before, but another important example is what's called a change of coordinates. If we have the same number of inputs and outputs, that gives us a square matrix. And the determinant tells us about the effect of this square matrix, the effect of this on area and volume and whether it preserves orientation. And we think of these as kind of remapping things. They tell us a different way to think about space. So here, for example, we've got a linear function with two inputs and two outputs that's expressed by this matrix, 1, 1, 1 minus 1. And what this does is this says, okay, our x and y coordinates can be re-expressed in terms of some new things, s and t coordinates, that kind of draw these two different new directions. And instead of using the old north, south, east, west directions, we can measure every point inside three-dimensional space in terms of this northeast direction and this northwest direction. So changes of coordinates come up all the time, and we're going to talk about them at some length later on in the course. Thank you very much.